A motor is the device that when connected to a battery converts electrical energy into mechanical energy. The motor shown above is used to lift a block of mass m at constant speed from the ground to a height h above the ground in the time interval delta t. The motor has constant resistance and is connected in series with a resistor of resistance R1 and a battery. Mechanical power, the rate at which mechanical work is done on the block, increases if the potential difference or voltage drop between the two terminals of the motor increases. Part A asks to determine an expression for the mechanical power in terms of m, h, delta t, and physical constants as appropriate. So, we know that power is equal to change in energy over change in time. And change in energy is equal to the work done on the system. So let's use an energy bar graph to find the work done on the system by the motor. Setting the 0 point for potential energy at the table, the mass starts with no energy. After the motor pulls the mass up, it will have Ug prime potential energy. This means the motor did this much work. The bar graph shows us that work is equal to Ug prime, and we know that Ug is equal to mgh. So, we can say that the change in energy is equal to mgh. This leaves us with mechanical power equals mgh over delta t. Part B asks, without m or h being changed, the time interval delta t can be decreased by adding one resistor of resistance R2, where R2 is greater than R1, to the circuit shown above. How should the resistor of resistance R2 be added to the circuit to decrease delta t? In parallel with the battery, in parallel with R1, in parallel with the motor, or in series with the battery, R1, and the motor. Before getting into the problem, I want to go over the elements I will be using for the real demonstration. Resistor 1 is a 14 ohm resistor, which I confirmed using the multimeter, although it displays a larger number because it has its own internal resistance of about 2 ohms. Resistor 2 is a 15 ohm resistor, again confirmed using the multimeter. There are 9 1.5 volt D batteries in series that power the circuit, and the mass consists of 3/4 taped together. Finally, the motor. Alright, now let's get into the problem. First, let's look at the time interval before R2 is added anywhere in the circuit. So, we need to add R2 into one of the 4 locations so that the time interval is less than 0.63 seconds. I will say now that the correct placement of R2 to minimize the time interval is in parallel with R1. But first, let's look at the other 3 options and see how they affect the time interval. When R2 is placed in parallel with the battery, it is effectively being placed in parallel with the rest of the circuit. This means that the current of the circuit is being split between R1 with the motor and R2. We can see here that the current through the motor when R2 is in parallel with the battery is about 0.4 amps. The current through the motor before R2 was added was 0.48 amps, but I lost the footage of that, but just trust me, that's what it was. Using Ohm's law, V equals IR, looking at just the motor, we know that the resistance of the motor is constant, but the current decreases. This means that the voltage drop across the motor is also less than before, meaning an increase in the time interval as observed. When R2 is placed in parallel with the motor, it splits the current going to the motor to now also go through R2. Looking at the multimeter measuring the current through the motor, we can see that the current is a little more than 0.4 amps. Using the same method with Ohm's law as before, the resistance of the motor is constant while the current decreases, meaning the voltage across the motor also decreases, giving a longer time interval as seen above. When R2 is placed in series with the battery, R1, and the motor, the total resistance of the whole circuit increases, therefore decreasing the current of the circuit, which is the same in all parts of the circuit since everything's in series. If we look at just the motor using Ohm's law again, the resistance of the motor is constant while the current through it decreases with the introduction of R2. This means the voltage across the motor will also decrease, which in turn increases the time interval. In the demonstration, the voltage became so low across the motor that it was unable to lift the mass. Alright, so now for the correct answer. When R2 is placed in parallel with R1, it decreases the effective resistance of the circuit. Using the demonstration, before introducing R2, the resistance of the circuit was 14 ohms from R1 plus whatever the motor's resistance was. When R2, with a resistance of 15 ohms, is placed in parallel with R1, the circuit's resistance is now about 7 ohms plus what the motor's resistance is. This is because of how resistance values are calculated when in parallel. Looking at the whole circuit, using a variant of Ohm's law, current equals voltage over resistance. The voltage of the circuit remains constant while the resistance decreases. Since resistance is in the denominator when it decreases, current will increase to the circuit. Now looking at the motor, using the previous version of Ohm's law, voltage equals current times resistance. The motor's resistance is constant, but the current is increasing, meaning that the voltage drop across the motor must also decrease, therefore decreasing the time interval and giving us our final answer.